Hey guys, this is the second part of this video looking at finite groups of order 30, and our goal is to construct a subgroup which has 15 elements. Okay, and what we know is that we have a CLOB 3 subgroup and a CLOB 5 subgroup, and at least one of them is a normal subgroup. Okay, and it was kind of like a counting argument we did. Right, let me try and summarize the counting argument. In the case where, so the CLOB 5 subgroups have 5 elements. There are 6 CLOB 5 subgroups. Well, their only intersection is just at the identity. So we have this kind of situation. Here's the identity. 1, 2, 3, 4. Everything looks like this. The last one. Right? So these are our 6 CLOB 5 subgroups. You can see that out of the non-identity elements, there are 24 of them. Right? Okay, and that was kind of what we did. So the 24 of those with the 20 elements of order 3 from all the CLOB 3 subgroups proved that you can't have 6 CLOB 5 subgroups and 10 CLOB 3 subgroups. Both of those things can't be true. Okay, so now we're in this situation where either P3 or P5 is normal. We can say one case would be that P3 is normal in G. Okay, and now we just need a little lemma. Really, it's 2 lemmas. So the first one is that let H and K be subgroups of a group G. Then let HK just kind of be kind of what you would guess, which is the products H times K, where H is in H, K is in K. Okay. And HK is a group if and only if HK and KH give the same products. Okay. In case you haven't seen this before, let's just try it. Really, we want to be, this is a subgroup. HK is a subgroup of G. Same thing, I guess. Okay, so we have to show that, if HK is a subgroup, then HK equals KH, and if HK equals KH, then HK is a subgroup. Let's suppose HK equals KH. We have to show HK is a subgroup. First of all, E times E is in HK, and that's just the identity. So E is in HK. So HK is not empty. And let's suppose HK and H1K1 and H2K2 are both in HK. Then we have H1K1, H2K2. Well, K1H2 is in KH, and by assumption that's HK. Okay, so K1, we can write K1H2 as, you know, what, H2 prime, K1 prime, and then so we have H1, H2 prime, K1 prime, K2, this is in K, this is in H, so this is H is in HK. Okay, so HK is closed under, as the identity element, it's closed under products. Also, we have to look at H1 K1 inverse. Well, that's just K1 inverse, H1 inverse. And again, we use the same trick. This is something in K times something in H. So this is in KH, which is equal to HK. Okay. So now our subset has the identity element, it's closed under products and inverses, so therefore HK is a subgroup of G. Now for the opposite direction, we have to show that HK equals KH. You know, let HK be an HK. We have to write this as like, you know, K times H. How do we do that? Well, actually, I guess there's an easy way. You know, what we can do is then H times E, that's in HK, since E is in K and H is in H. And E times K, that's also in HK. Okay. And now since HK is a subgroup, E times K times H times E, that's also in HK, but that's just K times H. I guess what we should say is that let H be in H and K be in K. And then this tells you that KH, well, K is in HK, H is in HK, so K times H is in HK. And what this says is that KH is contained in HK. And then there is one piece left, and that's to prove that HK isn't contained in KH. I guess that would be an exercise. Okay, so that's the first lemma. So now if we can only prove that P3, P5 equals P5, P3, well, that is easy to do if one of the subgroups is normal. So this is another lemma, I guess. You know, if K and H are subgroups of G, if K is normal in G, then KH equals HK. There's other conditions that give this, right? So if one of the subgroups is normal, then K times H is a subgroup. Okay, and we're in the condition where we know that either P3 or P5 is normal, so their product is then a subgroup. Okay. So let's prove that. Right, we have to prove that KH equals HK if K is normal in G. Okay. KH be in KH, then K is normal, so H inverse KH is in K, so write it as like K0. Okay. Now multiply on the left by H, so you get KH equals HK0. This tells you that an element in K times H can be written as H times K. So this tells you that KH is contained in HK, and the reverse direction is similar. So I'll just say similarly, or you can check it for yourself, but it's not hard to believe. You get that, QED. In particular, so back to our example now. So since P3 is normal in G, or P5 is normal in G, one of the two is true. P3 times P5 is a subgroup of G. Now this subgroup, what is going on with this subgroup? It has just the set P3 times P5 has at most 15 elements. Okay. So, but P3 times P5 has 15 elements. Right? Because you have 3 choices for the elements of P3. You have 5 choices for P5. So that tells you that at most 15 elements, right? To see that you have exactly 15, well, once you know that it has at most 15, like, if it had less than 15, it would mean like P3 intersected non-trivially with P5, but it doesn't. Okay, so therefore, take H equals P3 times P5 is a subgroup of G with 15 elements. Okay, that means any group you give me with 30 elements in it has a subgroup with 15 elements. Automatically that subgroup is cyclic. That's what we saw in class. Automatically that subgroup is normal because it is index 2 in this subgroup, in this group G. Okay, so just from this like arithmetic stuff, the arithmetic and the group theory, we automatically get this knowledge of the structure of a group of order 30. Okay. Let me leave you with one last note. Let's say note, let H and K be subgroups of G, then the number of elements of H times K, well, that's just the number of elements of H times the number of elements of K, right? Divided by the number of elements of H intersect K, right? So proof how do you prove this? Let's see. You just define phi from the Cartesian product of h and k to h times k, and phi of h comma k is just hk. By definition, phi is an onto function. Okay. Phi is not a homomorphism or anything. It is just a function. Well, what you do then is you show phi is onto. Well, phi is onto by definition, but you compute the number of solutions to the equation phi of hk equals g. And you show, or then you just have to show that there are this many solutions to this to each equation. Well, either this many or 0, basically. Okay, so you basically solve hk equals g for h and k. Okay, so like fix k, that tells you uniquely what h is, right? But only if, like only under certain conditions. I guess I didn't even want to do this proof, but you know, maybe think about it if you want, or don't. It's up to you. Okay, okay. Anyways, thank you for watching.